Okay, guys. Morning. Let's get started. So today is the third part of our density estimation discussion. So, as you recall, in the previous two lectures, we talked about histogram based methods, and then we talked about k-nearest neighbor algorithm, and then we introduced Gaussian models, both univariate and multivariate. So the mixture of Gaussian mixture model, or GMM, in order to find a better estimate of your data when you don't have any labels. So you're trying to understand some of the techniques you can apply on the unsupervised learning version. So today we carry on our GMM methods, and finally we're gonna talk about one of the optimizations as an extension of k-mean clustering, which is called EM, or expectation maximization. So let's see how EM can outperform k-mean in various means. All right. So let's just have another recap for Gaussian mixture model, or GMM. So we define J as one of the number of the classes 1 up to k So J could be 1, 2, or k, and normally we have k known to us, so k is given. So in conditional probability, so when we want to compute the probability of x, and x is a vector, so we have a lot of x's. So p of x given j, it's going to represent us a normal distribution, or a Gaussian distribution of x's in a multivariate version, and we have to define this normal distribution by their vector of mu and their vector of sigma, right? So the answer to this, so the distribution that this formula brings is going to be equal to the p of g of k, right? All the classes, k. So it's a joint probability distribution. So let Pj equal to Wj. So those weights corresponding to the probability of selecting bump j. So each of those bump are each of those separate distributions given each of the data in each clusters. All right. And we talked about the point that all the wj's are plus, so it's positive. And also the summation of all wj's must be 1. Because we normalize it in a way that the joint probability becomes 1, because you want to have your integral of px dx equal to 1. So if you have more than 1, you have to find a way to balance it. So also we talked about the estimate p of that x, which comes from the multiplication of these w's that we define with their probability, right? So we have k of those, 1 up to k, so you have to multiply this for all of those k clusters, so k time, and then we're going to have an estimate of the x here. And this is equal as if we multiply wj to the distribution, a normal distribution that these parameters define for us, the mu j and the covariance of j, right? And that's what we call it a Gaussian mixture model, or GMM. So we use this in order to put one step further than the Parsons window Poisson density window. And finally, in the class, we saw that this way of formulation needs to form to a maximization problem. So we want to maximize the likelihood of selecting and putting each point in its right cluster. So given D as our data set, x1 up to xn, so we wanted to find a Gaussian mixture model with these hyperparameters, which we call omega, wj, mu j, and ej, that is the best fit for our D. Right? So suppose you have some points here. And this can define these two distributions for you, right? And the distributions are known. So when a new point comes, you know that which of this distribution each new point belongs to, right? But say you don't have any known distribution, you just have some data. On the case of unsupervised learning, right? So you want to estimate the best fit for each of these cluster of points with a Gaussian model, and a Gaussian model defines by their mu and the vector of sigma, right? So in this case, you are doing the opposite thing. So you want to find the best Gaussian model that fits this data too. And that's why you can estimate two separate distributions here, right? You got the point here? So we are doing the opposite thing. So the distributions, the clusters are unknown, but the points are known. So we find the best fit for our points to come up, to use a Gaussian mixture model to come up with a new cluster. And that's why we call this. So we need to estimate this. It's case 1, and this is a different case, right? Case 2. All right. So how are we going to accomplish this task? So we want to find the best fit that is equivalent to the maximum likelihood solution, right? So we want to find the best fit that defines our cluster of points using a Gaussian model. So using the maximum likelihood solution, we know that the P estimate of the x's, x1 up to xn, is equal to the multiplication of all of them, right? So all the P hats of xn, and all of them should be maximized, right? And we saw that we can transform this and convert it to a minimization problem so that the minus log is minimized. So it's as if we are trying to minimize the in-sample error. And that's why the En came from. So minus log of P estimate can be defined as we always knew from the least square and linear regression, minus summation of log, all the logs of P hat xn, right? And then we know that this estimate, this probability estimate, comes from a Gaussian distribution. So the Gaussian distribution has these characteristics. So it defines a vector of x in higher dimensional space. That's why it's a vector. And we can define that with mu of that distribution and the covariance of that, right? So this becomes this with the weight. And then finally, we saw that this becomes, so this notation is called equal delta. So this means that this value, or the best fit, is defined to be this. So it's another way in mathematics to find equivalency, right? So we say best fit defined to En. And En is the summation of all of them. So this is equals delta. So now we define the problem of finding the best fit using the maximum likelihood solution, and we want to minimize the error that comes from this estimation, right? And then finally we stop at a point at how we're going to minimize this En of omega. So we got in a simple version, when you have one vector of x, so you have some x's, you want to find clusters for your points for which you want to find the best estimate of their distribution, and these distributions are coming from Gaussian's models. So mixture models, so we say GMM. So how are we going to maximize this to the real density of that? You have to find the En omega of that, and which is equal to the minus log of all the summation of WJ's multiplied this distribution, these parameters defined. So we want to minimize this. I talked about the minimization a little bit last session, but we stopped there. So one of the techniques you could do to minimize, just like least square methods or other optimizations we discussed previously, is to use a stochastic gradient descent. But the issue is this formula is very complex for a stochastic gradient descent to compute and calculate every time in order to converge, right? So instead of doing that, in the literature, people have been using an algorithm called EM, or expectation maximization. And that's what we're going to discuss here. Yep.
For the second line,
Mm-hmm.
we want to maximize the...
Yeah, so we want to maximize this. And then here we transform this to a minimization problem. So this is maximize, and here is going to minimize this. Right?
Is that the product of the probabilities?
Right, it's a joint probability, right, distribution.
So you want to maximize all of the probabilities?
So this is the estimate, if you recall. So this is the estimate of the probabilities, right? So we want to maximize the estimate of our probability. So we want to have the highest probability as our distribution. It's just as if we minimize the error involved with that estimation, right? So these two are equivalent in a form. Either we minimize the error or we maximize the probability itself, the likelihood, right? So this is the likelihood. So we want to maximize the likelihood solution or minimize the in error or sample error. Note that also there's a minus here. All right, so we reached to the point that we want to minimize En of omega, right? So I mentioned the issue with SGD is En is a complex function because it represents a distribution and it involves a complex formula. And we want to have the optimization in a way that we can iteratively converge to the solution. So that's why we use EM algorithm, expectation maximization. That's why we have E and M. It's an extension of the k-mean clustering. And it has two versions, soft clustering or soft decision, or hard clustering or hard decision. So today we talk about the hard decision, and then the next session we talked about the soft decision. So the reason we call them soft or hard is, in a hard case, if you recall, k-mean clustering was clustering the points using their center point, move 2, move 1, right? And it was using Euclidean distance in order to, when you had a new data like this, it was using a Euclidean distance to iteratively join that to the distribution. And this distribution must have been disjoint, so you couldn't have overlap between your distribution. So as an extension, EM in a hard version also conforms to the same rules, so you can't have overlap between your clusters. But instead of using only Euclidean distance, you are using a Gaussian mixture model in order to compute this distribution. So that's why it's an optimized version of k-mean. Not only use the Euclidean distance to your center point, but you use the distribution, the Gaussian distribution to that. On the soft case that we will talk about next week, we allow the clusters to overlap. So sometimes when you have data like this, right, you might have clusters, the first one and a second one. and these two are overlapping each other, right? So on the soft version, we allow that, but on the hard version, we don't. So we talked about both versions today and next session. All right, just like k-mean clustering, let's break the optimization into two subproblems. So subproblem number one. So given D, bunch of data we don't know the label, or a vector of data in higher dimension, x1 up to xn, suppose for each of those xi's within your D, we want to find the Gaussian distribution they belong to, right? So you have data, you don't know the label. So you want to find the best fit of distribution using a Gaussian distribution. That they can belong to. So we want to make sure this doesn't belong here or vice versa, right? So this is a subproblem number one. So let Bj as a subset of D denote the set of points sampled from Pjx. So we sample from each of them by this probability. We call them Bj. And then we use the Gaussian mixture model, defining by weight, the mu's and the covariance, the sigmas, for all the j's, to have this condition, nj is equal to the absolute value of Bj, right? All right. As you recall, in the Gaussian distribution, so for all the w's, we wanted to normalize them by their number because we wanted to have. So if we had 3 bumps, we wanted to have the overall equal to 1, right? The integral of px dx, we want to make it 1. So when you have n of those, you normalize them by n, and you find a w, each of those w's, w1, w2, w3. And for the mu j, you would do the same for all the n's, and you find a mean by the summation of all of those divided by the number. So that was the mean of each of those j's. So those points that we sample, we calculate their w and mu and also covariance, right? So we call it sample covariance. And also this is the sample weight as well, if you will. So in this subproblem, we have points from our data set D. We want to find a bj as the subsample of the points, and we calculate this tree that defines the Gaussian distribution parameters for us for those sampled. So sample mean, sample covariance, and sample W's, right? Just like this. So we have B1 and B2. So given the 6 point we had. Alright, so that was what the subproblem number 1. Let me just double down on this point. I mentioned verbally, but just to make sure you got the point here. So, in Gaussian models, when we do the optimization using EM, when we want to cluster using mixture models, we don't know the source of the data, right? But we just know the data here. We know some bunch of data and they're unknown to us. So they're like this, okay? We don't know the label, nothing. So in this D1, or if you want to have a D2, so just you have a bunch of data here and here, okay? So you want to cluster this. The only thing we have using mixture models or Gaussian mixture models is that we can calculate the parameters of the Gaussian distribution, right? When you have data, you don't know anything about it. What you can do is just compute the mean and sigma square or variance, or using this we can also compute the covariance, right? This is the least you can do. So when you compute the parameters of a Gaussian model, then using these parameters that you compute, you can guess whether a point is more likely belongs to each cluster. So say you define with 2 random clusters like this, then you compute the variance and mean, or covariance and mean, and then using this you can guess whether a point belongs to this cluster or the other one, right? Because they have to match. And that's what we do here. Otherwise, looking at this is just a flat set of, data with no other information. Okay, is that clear? So we define a subproblem number 1. Now let's talk about the subproblem number 2 that we need to discuss before going to define EM. So given the parameters we have here for a mixture model, W's, mu's, and sigmas, for J's from 1 up to K, we want to estimate bumps. So we want to estimate the bump membership. So each of those bump functions that I talked about, so each of 1D or in 3D, it was sort of a shape like this, right? So for instance, we want to find a PJ of X that is most likely to produce the X's, right? Now we are trying to guess the other side of the problem. When we have points, what cluster or what bump membership they can generate, right? So when we have this, we want to estimate what type of shape these two can generate, these four can generate. And we use a likelihood estimation here. So in a way, each of your xn's inside the subset of your data, which in this case you wanna call it bj star, which is the optimal bj that they can find. So j is the maximization of the likelihood. So the highest likelihood here, given your xn, just like the question you asked before. So here we want to maximize the likelihood that a bump can be produced by xn's, right? So how we do that? In Bayes' theorem, that's the fundamentals of Bayesian networks. So in Bayes' theorem, you have the joint probability distribution, and I'll talk about it in the next slide. Yep.
Sorry, can you just repeat what that says? J star equals R.
Oh, yeah. Argmax. So we want to maximize this.
Right.
It's maximization. So we want to maximize the likelihood to produce J given xn's, right? All right. So, all right. Let's see how we're going to compute this. P J given xn's. So there's a rule in Bayes' theorem, that forms Bayesian models. It's called MAP rule, so maximum posteriori probability. So that I'll talk about it in the next slide. Here. So the MAP estimate is an estimate of an unknown quantity that equals the mode of the posterior distribution. So you want to find the probability of a phenomena or something that happens to a distribution when you inject a new unknown to that. So when you have another data inside, what's kind of the probability distribution join form with that? That's why we call it posterior. So it's after you added that. So it can be used to obtain a point estimate of an observed, this must be quantity, on the basis of empirical data. So, for instance, in this case, using Bayes' theorem, so you want to estimate the J given xn, right? So this breaks into the P of xn given J for the class J divided by all the classes. So the probability of x1 given J P1, the probability of x Px2J P2, and the summation of all, right? And this is called the Bayes theorem.
That thing on the bottom is that's also equal to P of xn, right?
This point?
Yeah.
So, oh, sorry, this is from 1 up to k for all the classes. So 1 up to k. So P1, P2 up to pk. And also this is J. Sorry. Yeah, that's right. Yeah, I'll fix it when I upload. So this is J. So you want to have an estimate of an unknown when you put it inside the distribution. So what distribution comes after adding this unknown, right? And that's why we call it map estimate. And using Bayes theorem, you have to define it for each of those classes and divide the probability with all the classes. So now we found the two chicken and egg issue for our EM algorithm, subproblem number 1 and subproblem number 2. When we have several points, we don't know any information about them. So first we start with random clustering. Yeah. And also, let me just clear this so you have your... And this will be thus equal to the W of that class multiplied by the Gaussian distribution divided by all the classes, right? And that was J1. So in our GMM, both of them are from Gaussian distributions. All right, so now we finalize this lecture with EM algorithm, the hard decision or the hard cluster version. And I mentioned that in a hard decision, clusters do not overlap, right? So first we initialize with arbitrary bump membership. So we have data, we want a cluster. So we just randomly generate some bump membership for each of the xn. So we assign them to each of the arbitrary to each of those. Okay. Then we estimate a Gaussian distribution formed by this data. So using the parameters that we need in order to have a Gaussian distribution, W's, mu's, and covariance for all those j's. So in this case, k was 3, right? Close this again. Yep. So it's as if we use subproblem number 1 to find this. So we want to estimate the parameters of a Gaussian distribution given bump membership using subproblem number 1. So we have data. For instance, this is 3. And then now the other side of the problem. Now, given this omega that we found, the parameters estimate the bump membership given that. So it's just like an egg and chicken problem. So you start with arbitrary clusters. You find which of the points can be defined, belong to each of those clusters, and then after you add those points, you want to find the best estimate of a new set of clusters given those points again. So it's egg and chicken all over again, and you want to iteratively go repeat steps number 2 and number 3 up to convergence, right? So this was coming from the subproblem number 2, and this was the answer of the subproblem number 1. And after several iterations, at each iteration you can estimate your in-sample error, and then when you saw no further improvement, that's a sign that you converge. So after, I don't know, 5, 10 iterations. So that was for the hard decision. In the case that these clusters don't overlap, right? In a soft decision that we talk about next session, we see that we allow the clusters sometimes to overlap. So that's another way to cluster. Any questions for this? You got the idea? So you have points. First, you have to estimate a Gaussian distribution using these parameters. So first, you have to calculate the hyperparameters that can form a Gaussian distribution. And using these known parameters, you can calculate bump membership or a Gaussian distribution that they can belong to. And you have to repeat this again and again.
So it's like kind of like the k-means? So.
Yeah, it's just like a k-means, but it's an optimized version of the k-mean. In k-mean, your omega was only the center point. You remember?
Yeah.
So
the distances.
That's right. So it was a limited. You were using limited information in order to define your clusters. But here we use the information that we can use a Gaussian mixture model. So not only we use the center point as our Euclidean distance to each of the points, but we use a distribution using their covariance, their mean, and their double, right? So k-mean is a special case of EM. EM is more generalized. All right, so I'm going to stop here, and then on Friday, I'll have a recap of what we discussed on density estimation, and we talk about the EM on the soft version. And then, yeah, your software will be over on the density case. All right, have a good day, guys.